I think we're ready to go. Gusset, can you hear me?
Yes, Mari, I can hear you.
Okay. Hello and welcome everyone to today's session of Connection Wednesdays, where we'll be looking at an end-to-end workflow for the design of gusset plates using IDEA. Before we get started with the introduction, the actual presentation, a few preliminaries regarding the control panel, especially for those of you who are joining us with GoTo for the first time. You will find that there should be a control panel on your right-hand side. You can control your audio from there, your audio settings. But crucially, if you have questions or if you have any problems with either the feed or anything, then please post them in the text box from which I can see them, and then I can help you during the session. And we can collect questions as well that we can take a look at. So before we get started, my name is Marius. I'm part of the support team in the UK office. And joining me today is Gusset, the technical manager, also in the UK, who will be presenting the material. We can wait a little bit more for some more of our attendees to join us. I'll be handing over to Gusset to go over the agenda.
Thank you, Marius. Can you verify, Marius, that you can see my screen?
Yep, I can see your screen. I can hear you. It's showing the agenda page.
Okay. I will start in a minute. So I think that we can start. I see that a lot of people have already joined, so I think that the timing is perfect. So let me introduce you to today's agenda, where basically we're going to export a global analysis model into IDEA StatiCa Checkbot. And there I will use this model to identify and design groups of connections, which is basically a new feature that can speed up the design process a lot. Since we have picked a bracing that we will export into IDEA StatiCa member to be designed using the GMNIA analysis, and we're connecting this with gusset plates, unavoidably we're going to discuss some design considerations regarding this family of connections. Then in IDEA StatiCa member, we will fix the boundary conditions of the substructure to match the ones in our global analysis model. And lastly, we will show how to perform this advanced type of analysis. So since we have a lot of things to see, we will get started in a bit. Please note that this session contains pre-recorded videos, so to squeeze them into the time of this webinar. So you will be looking at a ridiculously big cursor and also some parts that are accelerated to make it. So let's start with our global analysis model, where we have prepared a fairly simple step structure. Please note that although this structure appears to be symmetrical at first, it's not, because, for example, the rafter on axis B is a single member. However, on axis C, we have split this rafter into two members. And I highlight this because the Checkbot export retains any definition we make in this global analysis model. Also note that this simple structure is fully designed, which means that every load case you would normally use in practice is defined. You saw the wind load cases, and these load cases have been used to create the combinations required by code. In this case, there are 247 combinations in total, including serviceability and ultimate. And also, this structure is fully designed according to the Eurocode provisions, and we can graphically see that every member passes the checks. In this particular case, to export the model, we need to go into the plugins menu and select the IDEA StatiCa Checkbot option. At this point, note that the process you're about to see is more or less the same for any of the supported global analysis applications. So now that we pressed the menu, let's wait for the checkbot window to appear. And to begin, we have to press the Create Project button. And what this does is that it creates a folder next to the global analysis software file. And this folder contains the model we're about to export, along with the connections and the members. And basically, you're free to share this folder with other project stakeholders. Now, since nothing was imported yet, we have to get back to the global analysis model. I will select everything, and then go back to Checkbot that is now linked, press the connections, and the import of the model starts. This part of the video is accelerated, although it does not take a lot. This is something that we improved in the latest release. And by default, we have the model with the member name labels active that are similar to the names in our global analysis software. Now, in our ribbon bar, we can activate and deactivate these labels of the member names, and even activate and deactivate the names of structural nodes. For your reference. And let's move to the wireframe model. And the reason we do that is because we want to see these red cubes, which basically indicate the location of potential connections. Please note what we mentioned earlier, that the member definitions are preserved. So on axis C, I have a single member. On axis B, I'm sorry. And if I move on axis C and I touch the members with the cursor, I can see that these are highlighted. We have two different members. Clicking on the first member shows its properties on the properties panel. And if I hold down the Control key and I select the member that follows this one, that is an extension of this member, I can select the properties of these two. And in this case, I'm going to raise this member a bit in order to have the flanges aligned with the lateral beams. So I'm changing the set value, and I have effectively aligned these members, which is important to do proper connection design. Another important thing is the loading. So I'm going to press the Loads button and display the dialog box showing the load cases and combinations that have passed through the beam link. Now we have two columns, and in the second column of the dialog, we're looking at the result classes, which are basically groups of combinations that we use to design either members or connections. Checkbot automatically creates the all ULS combination grouping, And by clicking at the label of this group, again, we can see some of its properties, like its name, that we can change. But most importantly is the option to evaluate critical effects, which is activated. When this option is active, this means that for this connection grouping, that when we design a connection or a member, the software automatically detects the members that have extreme stresses and extreme internal forces, and only passes the combinations that cause these extremes to the substructure to be analyzed, essentially saving a lot of time to the designer that does not have to go through all these combinations. Another interesting option is that when the user, for example, selects cube and then presses the draw button on the ribbon, depending on the internal force that he has activated, we can see at the diagram of the connected members, the internal force diagram. We can show internal force diagrams for individual combinations or for the all ULS result class, which shows the minimum and maximum diagram on its member. So now let's move to the design of group of connections, which is something new. And to help the user identify connections, by default, Checkbot classifies all connections into typologies and arrangements. Basically, right-clicking on a typology or arrangement brings up this menu where you can select all connections that belong to this typology. So in this case, we have base plate with a single column. And then I will try to design a group of joints that contain the base plate with the bracing diagonal. This is essentially the corner joint that I click to detect on the tree of connections. So this is connection C9 that is highlighted. And now I can select all connections in this arrangement, but to design connections, we need to have a reference connection, which is the one that is selected first. And this is the connection that will contain the reference geometry, and the rest will get the properties from this one. Now the parent connection is C9, and holding down the Shift key, I have selected the rest of the connections. Now I will right-click on the selection, create a group, and I will click on the group name to see its properties, change the group name to a name that makes sense, like detail 1. And in the properties of the group, I can see the reference connection. I can select the reference connection by this icon, or even open the reference connection to design. And I'm also looking at some statistics. I can also display the named groups by pressing the groups button in the label. And here I can see that all corner base plates were identified. So let's select the reference connection and let's open it into IDEA StatiCa connection in order to design it. Please note that the column and the bracing passed through the link, but what's more important is that only 10 combinations passed through from the 247, because these are the extreme ones, the critical ones. To model the connection components, I will press the pause button and I will use the connection library and use one of the proposal I have already created. Now I can change some settings of the proposal, but I will not do that. I will press OK. And when the template is applied, I can now see operations, and I can click on any part of the connection and change its properties like I would normally do. A very Interesting new feature we have in version 24.1 is bulk changes on the model by selecting the operations label. And here I can, for example, set the plate steel grade to S275 for every plate in the connection, or set the weld sizing method to capacity estimation. And then by pressing the weld sizing button, the software initiates the calculation of the connection. And the reason we do that is because after this calculation is over, it will take the results and apply a machine learning model we have developed that will calculate every connection, weld to its capacity. So let's wait a bit for this segment. And everything is okay. The configuration appears to be passing all checks, and please note that it's supported, the Gusset is supported on 2 edges. It's very important, as I have initiated the buckling analysis. So again, this part is slightly accelerated because we have too many combinations. And here we have an amplification factor of 26.46, which is way over 50, which is the limit of the Eurocodes. Let's also display the buckling shape for this. And basically, this would normally mean that everything is okay. But is it? Yeah. Well, let's dig a bit deeper. And to do so, we need to get back to the design, select the member, and set its model type to NVYZ. To understand why we have to do that, we need again to get back into our global analysis model and check the bracing. So you see that in our global analysis model, we have set the bracing as a member that only resists axial forces, and basically setting the model type to NVYZ is something slightly similar, not the same thing, but similar. And now let's initiate once again the calculation and the buckling analysis to see how this change influences the analysis. So we need again to perform the buckling analysis. And again, now here, surprisingly enough, we have a different result, which is a low value. It's 6.65. The difference is a lot, and we need to investigate this further. So first, let's save this model and return Checkbot, and then let's go to another slide and start discussing a bit about Gusset plates. To add some context to the discussion, I will start with an article that was published in the New Steel Construction magazine for the design of Gusset plates. And this article was, unfortunately, it was released after a failure of a relatively long Gusset plate connection. So the SCI looked into this family of connections and published some provisions, some guidance. The thing is that although Gusset plates are seemingly simple type of connections, there are a lot of concerns regarding them. And the bottom line, I don't want to go through every concern that is discussed in this article. I have outlined the concern here just to show you how important it is to correctly assess this type of configurations. So in IDEA StatiCa, we have the linear buckling analysis. However, the results of this analysis are not reliable when investigating the buckling failure modes. It's not that this type of analysis is not reliable. It is a reliable type of analysis. The thing is that its results cannot be applied on this specific family of connection. The problem is that in IDEA StatiCa connection, we don't have the context of the surrounding structure. And this is the reason that we need to make assumptions. So, for example, we need to change the model type of the bracing to NYZ. There is always the option to maintain a critical factor over 15, which is the Eurocode recommendation, which is a very safe option. However, this leads to an over-design of gusset plates. Now, if we want to go below the value of 15, it is unclear which limit is safe for any gusset plate. Another thing that's important when we discuss gusset plates is that their slenderness influences the behavior of the connected member. So if the critical axial force of the gusset plate is lower than the critical axial force of the member, then we might have a compressive system that sways on gussets. And we don't want that because in this case, the effective length we have calculated in our global analysis software is significantly different from the effective length of the member that we're expecting, that we have assumed originally. So if we want to be sure, the best way is to use IDEA StatiCa member and perform a GMNIA analysis to have a reliable answer. And this is what we're going to do in this webinar. So let's get back into IDEA StatiCa Checkbot, where we're looking at the results of connection C9. And in order to be able to apply to all members of the group, we'll right-click on the group label and press the calculate button, and the software initiates the calculation. We see that next to our connections, instead of having an icon, we have an hourglass. This means that a connection model is created behind the scenes, and the reference connection geometry is applied on the rest of the models. And as the results become available, we see that we have a check mark next to the connection. In this case, it's green, meaning that every check is passed, but we have a different icon if something does not pass the checks. And then by clicking on the members of this grouping, we can see the results in the properties panel. Next, let's go and discuss productivity thing, which is basically how we deal with one of the common challenges that we face as designers. Now, in this node, for example, we have two closely spaced nodes. We have the bottom node with the bracings and the top node with the beam. However, since these are too close, I want to merge them. And I will right-click on the bottom cube and delete it. This does not delete anything, it removes the connection. And then I can click on the top cube. In its properties, I'm looking at the connected members. And by clicking at the arrow and holding the control key, I can select additionally the bracings, press the arrow, and the bracings are now part of the connected members of the top connection. Now let's press the open button, and this will open IDEA StatiCa connection, and we can see that the diagonals are part of the connection. Let's have a look at the wireframe model, where we can clearly see that the sticks that denote the diagonals are below the fictional node. This means that they have eccentricities, and if I click on the members, I can look at the properties that the eccentricities were added, which means that these eccentricities will also influence the analysis. So now let's change the model type of each member to NVYVZ, because this is the right thing to do. And again, we will use the connection library to model the geometry of this connection. Now the connection library on. Unfortunately, since this is too complex, we do not have any option, and this is the reason that we're going to use the connection library on a selection. We will apply it partially. So I'm selecting the beams and the column, pressing the check button, and now I have some options. I'm clicking on the first and applying the first template. Let's go with the default. And then we start to apply partial selections for the bracings. Again, let's apply for the horizontal bracing a selection, press the check mark, and we can see some options. Let's go with the second one this time. At this point, we will see a warning, but I will show you how to fix it later. Again, a selection for the vertical bracing, press check mark, and I have some proposals here again. Let's go with the second option. And after the application of the template, let's close this. And we see two warnings on two plate cut operations. And we have to go to each of these operations and play around with their properties. So they have incorrect work plane definitions. So we're fixing that. The first connection is okay. Let's move to the other one and change the work plane definition again. And this is it. The connection is now ready to be solved. So let's press the calculate button. Again, this part of the recording is also accelerated. At this point, let's also note that since we have more connected members in this connection, we have more combinations, more critical combinations. We also moved the buckling analysis. The rest of the components were okay. And again, we have the results of the buckling analysis, where we have an amplification factor of 4.99, which is very low according to what we have discussed. Please note that let's display the buckling shape first to understand where this buckling factor comes from. And this is clearly due to the vertical bracing gusset plate, which is this dangerous type of gusset that is connected on one side. And this is the reason that it has a lower buckling value than the other end of the connection that is connected on two edges. Since we're going to export this into IDEA StatiCa member, I have to detect the critical combination that corresponds to this buckling factor, which is this one, and I will use it to go to IDEA StatiCa member. So let's close this model and get back to IDEA StatiCa Checkbot. And before we move on to the next part, let's do a quick poll. Basically, we would like to know how often do you design eccentric cast plates that are supported on one side only? So we will keep the poll open until most of you have answered. So Marius, it's up to you.
I think I'll close it shortly. We've had about 2/3 give us an answer. As it stands, it looks like it's split between yes and yes, but sometimes. I'll close it for now so that we can proceed.
Okay.
And I can share the results so we can take a quick look. But essentially, most will either design some form of eccentric gusset plate supported on one edge, or will have to, essentially because it's a project requirement.
Definitely, yeah. So the thing is that people design this type of gusset plate. So it's very important to have tools that help them to correctly identify their influence on bracings.
Yep.
That's interesting. Interesting outcome. So I'm not sure if you can see my screen.
Yep, all good. Back to the presentation.
Okay. So let's start with the export to IDEA StatiCa member. In order to do the export, we need to identify the minimum substructure that we need to export. And in this case, besides the bracing, we're going to export the column that contains the two closely spaced nodes. And in this case, I have defined the same connection as in the other side, but I have not merged the nodes because we have to export into IDEA StatiCa member. And you can see that the top connection and the bottom connection basically contain the definitions, but they are not a single node. This is easy to do with the connection library, and one of its advantages. Let's also discuss about result classes, where I have created a result class that contains the critical combination that we need to export. And the next step is to define the substructure. So I'm selecting member and hold the control button. I'm selecting the analyzed member, then press enter. And let's fold the connections. And now below the connections, I have a new category named members. So I'm selecting the member. I'm setting the result class for check, the new one I have created, updating the load. And then I'm going to open this in IDEA StatiCa member. So see that in IDEA StatiCa member, we have the export of the substructure where we have our analyzed members, which is the bracing and the column. We have the related members that are the members that constrain our analyzed members. And of course, we have every connection component and the structure loading. So let's go on and perform a quick calculation to see what will happen. So we'll start with an initial material nonlinear analysis. It's very useful, as you would see, as a first step. And after the analysis is over, let's display this wireframe model and go on to display the internal force diagrams. Let's display the axial forces, and surprisingly, we see that there is no axial force developed on member M3. Now, this is the reason we need to go back into a global analysis model and see how this deforms in order to match our boundary conditions. So let's first isolate the structural part that we have exported into IDEA StatiCa member, and then display the deformed shape for this specific combination. And in the deformed shape, we can basically see that the rafter moves along the global Z direction. Another thing is that the frame remains constrained in the Y direction. Let's also have a look at the axial force diagrams to know what we have to expect. So we have about 68 kilonewtons for the horizontal bracing and about 39 kilonewtons on the vertical bracing. So let's get back into IDEA StatiCa member. And first, we're going to change the related member support to match the definitions, the boundary conditions in a global analysis member. So we'll start with member M16, and we will release the Z direction because this moves freely. Then we will proceed with members M25 and M28. We will also fully release these members. We will be only supporting them along the Y-axis, the global Y-axis. Then, for the horizontal bracing, we're going to release the local X direction to let it deform axially and develop its force. Another thing we need to look at is loads, because we see that there are some load concentrations that are probably erroneous. So we can detect them in our loads and delete them. So I'm removing this. And as I remove this erroneous definition, I see that the rest of the loads come into perspective. And lastly, I'm going to apply the load to the full height of the M2 member. And again, I will go on and press the calculate button to again calculate the structure and display the axial forces and see and assess. Okay, so let's again activate wireframe model, activate the internal forces, and we see that we have a perfect match. I have a 68.9 axial force on the horizontal bracing and 39.3 compression force on my vertical bracing. So I have to go and perform buckling analysis. Again, the buckling analysis is only an indication, and it is required because I want to identify the critical buckling shape, and you amplify it and use it as an imperfection for the GMNIA analysis, which is basically the only analysis that can account for all these effects in gusset plates. So let's wait a bit until the buckling analysis is over. And here, surprisingly, we see a very low buckling factor, 1.29. The buckling factor is relevant for the buckling of the member, as we can see. So the bracing buckles out of plane. We can also have a look to some other mold shapes that are available. So we also have the second mold shape, which is similar to the first one, third mold shape, etc. So we're going to use first mold shape. Basically, we're going to amplify that and use it for our GMNIA analysis. Now, to perform this amplification, we're going to use the Eurocode provisions. Now, since our bracing is a circular hollow section, it's hot finished. So the buckling curve for any direction is A, and then according to the buckling curve and the type of analysis, we're getting the design value of the initial local bow imperfection. To get the imperfection, we need to know the member length, which is something trivial, and basically we have an amplification factor 24.88 mils that we need to apply at the buckling shape. And this is something easy. So next to my buckling shape factor, I can add the imperfection amplitude 24.88. Please note that after pressing enter, the value will be rounded, but only the view of the value is rounded. The software maintains the full definition, and the way we view the values depends on our settings. And of course, I can enter imperfections in any other mode shape. But let's go on with the GMNI analysis. So I press the GMNI button and calculate. And we're waiting for the software to do its magic. One thing that it's noteworthy is that in IDEA StatiCa member, you can amplify more than one mode shapes at the same time. However, there are no recommendations in the literature about that, so we don't have any recommendations for you, but the software is ready in case something is published to be used. And now that the GMNIA analysis is over, I can quickly see in my graphical view and in my results table that the plastic strengths are everywhere below 5, and this means that this design is acceptable. Let me also activate the mesh to see how this deforms. And let's also have a look at the bottom gusset plate that's supported into edges. So that was it. And before we close it, let's revisit some of our gusset plate design considerations in IDEA StatiCa. So when you're using IDEA StatiCa connection and you have a bracing that's connected to the gusset plate, always set the member model type to NVYVZ. As we have demonstrated, this has a significant influence on the buckling behavior of the member. Now, when you want to perform a full design, but you don't want to go into IDEA StatiCa member, what you can do is try to enter an additional shear force to the critical, to the case that's critical for the design. The magnitude of this shear force is 1/10 of the axial force, and it should be applied at the direction of the gusset deformation, as I'm showing in this picture here. And of course, if you're going to use this approach, you should make sure that the shear force is applied at the center of the bolt. One last thing is that when we cannot avoid designing gussets supported on one edge, which seems to be the case as many designers are forced to design this configuration, please use IDEA StatiCa member GMNIA analysis to verify the behavior of the overall bracing system. And before we move to our Q&A, the key takeaways is that we have developed a tool called Checkbot. So you can communicate your designs, and besides communicating your designs with the other stakeholders of the project, you can streamline and accelerate the whole steel design process, as you do not have to go through tables of forces, identifying critical combinations and stuff like that. This is something that can be taken that is automatically happening. We have tools to quickly and efficiently analyze even the most demanding structures by easily applying an advanced type of analysis. And what's more important is that the results are intuitive and interpretable. The results are graphical, and you can check any step of the calculation. So I think that we nailed the time. So let's move to the Q&A session. I'm not sure, Marius, if we have questions.
Yep, we have a few questions that have come up, which we can take a look at now. The first one has to do with.
Let's keep it for 5 minutes. Answer the most, pick some that we can answer, and we will get back to the attendees with an email, maybe answering all of these questions.
Yeah, so I've addressed them directly as well. There are a few, but yeah, if any questions come up after as well, just send them to support, and I can either me, Kosti, or Nefeli can take a look. But from the questions we had during the session, the first one has to do with welds, and specifically the machine learning approach you used for the optimization. So the question is, why do you need machine learning to design welds? AI is statistical, not 100% accurate.
Well, basically, we don't need machine learning to design welds. We have designed welds for many years. The thing is that since engineering designs are based on several design iterations, we can use machine learning and have an initial guess that will save you a lot of time, effectively reducing the required design iterations. The second thing is that in this case, we're designing to capacity, which means that effectively we don't need many design iterations. Okay. So I'm not sure if this answered the question.
Yeah, just to add, essentially, It's for the optimization. It's used there, and it's used to kind of establish what geometry would be potentially suitable based on data we have available. So we're kind of estimating what size might be appropriate for the criterion we're using, and then the code check actually happens as it would normally, standard code checks. Another one is, how do you analyze a bracing connection with only a single bolt? This one I haven't addressed yet. So if I don't get to send you a response here, I'll email you. But yes, I think this might be interesting. It's relevant to this topic as well.
Okay, yeah. Basically, we follow the, let me get the slide back. Basically, for a connection with a single bolt, the recommendation here is what you need. So since we're 5 minutes past closing time, let's answer one more question, Marius, and let's close this.
Yep,
here.
Sounds good. There's another one, and I think I've tried to address this as well. I think I've covered it. It might be useful for others listening in, because I know that this terminology is used, so it might be good to clarify. So there's a question regarding GMNIA. So it says, you mentioned GMNIA analysis. Is it similar to GMNLA? Do you have any reference paper for this, and which algorithm is behind it? I had a quick look as well, and I think the analysis type you're mentioning, GMNLA, I think it refers to nonlinearity in terms of geometry and material, whereas GMNIA is essentially nonlinear in both those ways as well, but it also includes imperfections, and that's the sort of next step, as it were. So you're using some buckling modes that you've established, and you're applying an imperfection so that you have this sort of initial deformation in your structure, and you take into consideration, a sort of reduction in capacity as a result of this sort of initial imperfection. So if I've understood correctly, GMNLA is a sort of step before the analysis type that's being done in this demonstration. GMNIA will include an imperfection, and therefore will account for some of these buckling situations more accurately, hopefully, if you've used appropriate imperfections. I don't know if there was anything you wanted to add to that, Gusset.
No, I think this covered everything.
Okay, yeah. So the confirmed is so I think that's the key difference. So just bear in mind when you're looking at that. I can, if there's anyone that's interested in sort of exploring that a bit more, just email us at support, and I can send you links to the article that covers it, and it also refers to Eurocode guidance that essentially contains the references to these types of analyses and what the prerequisites are for your analysis type to be classified as that type. So in terms of time, do we have any more time, or should we close it here, Gusset?
I think that we should close this, so we don't have too much time. So thanks everyone for attending. We hope you found this interesting and useful, and hope we will see you in the next one.
Yep. Thank you for joining us, and enjoy the rest of your day.